will have a very interesting lectures to follow. I will just start with the first lecture. I request before I request Professor Jie Han from Kansas University, US. I have pleasure in reading out his giving his brief biodata. Uh, professor he is professor of geotechnical engineering in civil environment and architectural engineering department at University of Kansas. He received his PhD degree in civil engineering from the Georgia Institute of Technology in 1997. Professor Han is the sole author of the book titled Principles and Practices of Ground Improvement and has published more than 400 peer-reviewed journal and conference papers. Professor Han is an ASC Geo Institute Board Governor, a council member of the International Geosynthetic Society, the current chair of ASC Geo Institute of Soil Improvement Committee, and the current chair of TRB Transport Earthwork Committee. He served as an associate editor of the ASC Journal of Geotechnical and Geoenvironmental Engineering and ASC Journal of Material in Civil Engineering. He is editor of Transportation Research Record. Professor Han has been invited to give more than 200 keynote invited lectures and short courses around the world, including the State of Practice lecture at 21st Annual George F. Sowera Symposium in Atlanta, Georgia. In 18th, during the 18th UK IGS lecture in London, 2018, and keynote lecture at the Geo Americas International Conference 2020. He has received numerous awards from professions, including but not limited to the 2011 Samsed Prakash Prize for Excellent Practice of Geotechnical Engineering. The 2014 the International Geosynthetic Society Award, the 2017 ASC Martinez Cap Foundation Engineering Award, and 2018 ASC Kansas City's Section Engineer for the Year Award. So I am sure that with so much of accomplishment, you are all eagerly waiting to hear from Professor Han, and I request Professor Jie Han to deliver his lecture. Professor Jie Han, please.
Good morning. Thank you very much, Chair, for your kind introduction. It's my great honor to give this lecture at your conference. I also like to thank Professor Randy and Professor Babu, and I saw Professor Rao on the screen, and he sent me a message as well. I really appreciate it. I have a lot of friends in India, and I also like to thank Professor Anand Pupala, one of the best friends in US, and we have worked together so much. I prepared the presentation for 35 minutes, but I will try to finish within 20 minutes. My topic will be on the limit equilibrium analysis and design of geosynthetic-reinforced field walls under special conditions. So here basically is the outline of my presentation. I'll start with the introduction, give you some background. Then we'll talk about the limit equilibrium, and then I will focus on the unified design method for field walls and the slope under special conditions. At the end, a few concluding remarks. Then I'll share with you the Asian reinforced field wall built in China about 1,000 years ago. This is basically built with natural material and use like a tree branch, use the grass, basically place layer by layer. As you can see here, those are the layers. And between that, basically is the field material. Okay, but back 1,000 years ago, Chinese people already know how to build a retaining wall with reinforced technology. Now, the modern reinforced field wall with steel reinforcement, typically we refer back to 1960 by the French architecture engineer called Henri Van Damme. And he developed a technology basically uses steel reinforcement. As you can see, this is reinforcement layer by layer and with field material between. And the different from the Asian technology, he added the facing here, okay, to protect from rain erosion, wind erosion. But this is the one of the earliest retaining wall built with this technology. As you can see, this is facing. But the problem after you add the facing, where the water can go out, if you cannot discharge the water, will create a poor water pressure behind retaining wall that will destabilize the retaining wall. This is why it's important. Behind the retaining wall, you need to have drainage layers. Okay, those are stone layer, basically drainage layer, discharge the water, reduce the poor pressure. But we also can use geosynthetic. That's the one I want to focus on today. The picture show you here, basically with the uniaxial geogrid, and also place layer by layer with backfill material between. And this is using a modular block technology. You also can use a panel system, connect with geosynthetic or with steel reinforcement. But how do we design retaining wall? Typically, we treat this as a rigid block, and then we say, there's external stability with earth pressure. And then we have a lateral sliding, overturning, bearing capacity. We also need the design for internal stability. Basically, this is a failure plan. Typically, we use a Rankine or Coulomb failure plan. And then in front of the failure plan, we call the active zone. And this is a basic passive zone or stable zone. And we also have earth pressure, basically transfer the load to the reinforcement. And the reinforcement will carry the load, basically stabilize this wedge by tension. But typically, we require the tensile strength of geosynthetic and also require the anchorage from the geosynthetic. Now, at the front, also, we need to have a connection to make sure everything stable. Okay, but that is a basic design used called lateral earth pressure distribution method. Now, if we look the slope stability is a Bishop-Spencer method. Let me start with the Bishop method. For unreinforced case, you probably know use a circular slip surface, and then we basically calculate the fact safety based on the resistance moment divided by driver moment, right? How do we consider reinforced slope? We have a reinforcement here, then we have a tensile resistance. Then we add that into the calculation. This is the soil moment resistance, and this is tension from geosynthetic. Then multiplied by the arm, they get the basic resistance from geosynthetics. Okay, but we also can use the Spencer method. We can get like a wedge failure plan instead of circular failure plan. I will mention both methods in my presentation. Okay, now let me talk a little bit about analysis versus design. A lot of time we consider they are same, but really there's a little bit different. The analysis typically say based on the refer to the calculation of performance index for stability purpose. Typically we talk about fact safety. But based on the assume the non-layout tensile strength of geosynthetics. For example, like this one. We typically have a slope. We know the slope height, the slope angle. Then when we place the geosynthetic, what kind of length, spacing, tensile strength. Then we run slope stability to calculate the fact safety. Okay, that is the approach called analysis. We can have a different length, we can have a different spacing, we can have different strengths. Really, you can basically try the error process to reach the fact safety. You can have a multiple different answers. Okay, if you change your length, change the spacing, you can get another answer. Now, for design, it's a little bit different. Design is referred to calculation performed to determine the layout or tensile strength of reinforcement to meet the performance requirement. For this case, I use a retaining wall. Typically, we know what the requirement for retaining wall, fact safety, internal, external, and tensile failure, those kind of things. But a lot of time we know the spacing based on the facing block of panels. But we know the spacing, we know the required fact safety. Based on earth pressure, we can determine what the tensile strength is and then what the length. Okay, but step by step, there's only one answer. There's no multiple answer like slope stability. But there are two different methods we use in our practice. Okay, now in most countries' code, how to divide the retaining wall and the slope based on the angle. If this angle is greater than 70 degrees, that's a retaining wall. there is this angle less than 70 degrees, this slope. However, the two methods used for those structure design very different. As I mentioned earlier on, this use lateral earth pressure method. Basically, this distribution. Based on this distribution, as you know, the lower layer carry higher force because you have a triangular distribution, and this one will have a lower force. Now, if you use slope stability, if you have enough length of anchorage, all the lengths will have the same tensile stress requirement based on the fact safety. Okay. Now, people may argue the limit, the lateral earth pressure method also limit equilibrium. Just try to differentiate between those two methods. I call this a lateral earth pressure method. This is a limit equilibrium method. Okay, for slope stability. Now, the problem is, how does the earth structure know when it becomes a wall or slope? This is basically artificially divided by people, not by earth structure itself. Okay, now this is the one earth structure actually in India, close Himalayas. And some of you may recognize this one. And as you can see here, this is very steep walls and then getting flat with slope. I'll show you the cross section. This is for the airport, basic scheme airport, and the runway. And this is basically retaining structure here. Okay, this one also subject earthquake 6.8 magnitude performed very well. If I show you the cross section, you see that they change the angle here. The bottom, if you base on the 70 degree, this is wall. On the top, this is the slope. How do we design? Which method we should use? Is a wall, a lateral pressure method, or slope stability method? Okay, that would be challenge. Okay. Now, there was some research done by others, like Allen, Bethard. They measure quite a lot of retaining wall, basically instrument that measure the tension in the geosynthetics, and they also monitor the slope. This is a greater than 85 degrees, this is less than 70 degrees. Actually, the distribution of tension with that, if you compare those, look very similar. There's not much different. Now, magnitude-wise, slope maybe require less tension. Okay? But here basically show they have a very similar tension distribution. But ASHTO this year, 2020, this why my talk is very, very new. Actually, now suggests 4 different design methods for retaining wall reinforced slope. This is called coherent gravity wall method for steel reinforcement, stiffness method for geosynthetics, simplified method. Basically, this is a lateral earth pressure method for steel and the geosynthetic. The last one, limit equilibrium analysis, geosynthetic reinforcement. But this method also can be used for compound failure. Okay, but that is the one I want to focus on today. We have done quite a lot of research on this topic. Now this method has been included in the ASHTO new design specification. Okay, Professor Yang did some comparison with different methods. As I just mentioned, that this is basically a lateral earth pressure method, ranking or Coulomb, and this is the limit equilibrium method, and this is the finite element method. This is the K stiffening method. But this is a measured tension from geosynthetics. Actually, limit equilibrium method come out pretty close to the finite element to the measured data. Okay, a little bit overestimate from here. The limit equilibrium method has performed very well. This is for retaining wall situation. Now, today I want to talk about 4 different special conditions. One called tier walls. Basically, there's a one low wall, there's a steps, and another wall you can have more steps. Okay, and another case dealing with back-to-back walls. You have this side wall, this side wall. This is mostly used for bridge abutment. And another case dealing with called limit space. This one may be like a bedrock. We build the narrow geosynthetic retaining wall in front. And then this is like a secondary reinforcement. You have a primary reinforcement with a stronger, longer one, and then a shorter one. Okay, basically try to improve the connection between the facing and the reinforcement. How do we design for those kind of situations? Okay, that is challenging. The typical retaining wall design method cannot directly apply to this. Okay, now before we talk about those methods, let me show you the relationship between wall and slope. I call a progressive failure. Let's start with this vertical one. Let's say if we apply the load at the rest, okay? If at the rest means there's no movement, right? This earth structure will be stable. How about if I reduce the load less than P naught or K naught, and the soil start to move, and typically you move gradually from the facing in and in, and there's 0.3 H. For some of you designed for retaining wall, you are made familiar with this 0.3 H. This is typically used for steel reinforcement design because steel reinforcement is stiff and they only allow small deformation. This is why the failure plan will develop around this surface. Now, if we keep reduce the load up to active earth pressure, then this basically ranking failure plan will develop 45 degree plus 2. But this is the failure plan we use for geosynthetic reinforcement because it's flexible, allow more deformation. Now, how about if I keep reducing the load less than KPA? Of course, this will not be stable because PA is the minimum load to maintain the stability. That this wedge will slide down. Okay. How about after slide down, then even though you don't have a force to push this one, this wedge is still not stable because this angle is greater than friction angle of soil. This continues slide down and up to this point. Until the slope angle is equal or less than friction angle, that becomes stable. As you can see here, this is really the progressive process from a wall gradually going to steep slope and going to flat slope. They are really the same earth structure, just at different angles. Okay, this is the linear equilibrium method for the wall. This is the linear equilibrium method for slope. Okay, now let me show you whether this is real in the physical real situation. This is the wall facing here. Okay. But this is the line 0.3 H happened, and then this is the line basically 45 degree plus by 2. For real retaining wall structure happen like this. Gradually, as you see, the failure plan gradually. If you allow the movement, eventually the whole thing will just keep going down. Okay. Okay. But actually, we already have used those two together. If you use the numerical method, for numerical method, typically we don't distinguish between wall and slope. There's one technology called shear stress reduction technique, right? You divide the cohesion by fact safety, divide the friction angle by fact safety, and then you plug it into this numerical method. And then you run the stability until the point reach your limit equilibrium. The fact safety is the corresponding fact safety, minimum fact safety. So it doesn't matter this wall or slope. We have been doing that already. The numerical method is applicable to both wall and slope. It is a unified method. We don't need to distinguish them. Okay. I've been working with Professor Dov Linshinsky at the University of Delaware back like now it's 16 years ago. We start with the vertical wall and we use different method. We use the Bishop method to dealing with vertical wall and the ranking numerical method. Now, numerical method ranking, actually the failure plan very close. Now, all those cases, the fact safety equal to 1 by the equilibrium. Now, the Bishop method is a little bit away from this surface. But then if we use Spencer method, then actually it's pretty close because the Bishop method is always circle. You cannot get exact failure plan. If we dealing with slope like 70 degree, actually they match pretty well. Bishop method and the numerical method. Okay. The numerical method, limit equilibrium method had lead to similar results. Now, how about tear wall? That's a special condition we talk about. Now, as I said, really it's difficult to use the ladder earth pressure method to design tear walls, but Federal Highway modified the method. Okay, consider 3 different conditions. Let's say if the offset is very small, they treat it as a vertical wall, just one wall. If the offset is larger than the failure plan, they basically say they are independent walls. Now, in between, they have some way to handle basically linear interpretation between that. But this is basically based on the concept, okay? Geometry derived whether this is real or not. But we check out that use numerical method and the Bishop method, okay? From this case, as you can see, for the 3 tiers, numerical method, the Bishop method is show exact failure plan. It's not exact same as that. Let me show you more about the results. But here, basically based on the Federal Highway Design Guideline, okay? But this is like a one wall, and this is like an independent wall, and then between they're linear. But based on the case, we had two different soil, one with a low shear friction angle. I'm sorry, this is a 1 tier, 2 tier, 3 tiers. Actually, we find out at 0.8 H, actually they become independent. And also require strength lower than the Federal Highway Design method. But in other words, the Federal Highway method based on the concept is not the exact right. Overestimate interaction distance and also require tensile strength situation. Okay.
Professor, 5 minutes, please.
Oh, okay.
I'm sorry, before I get carried away, I think I should warn you.
Yeah. I that's fine. I prepared for 35 minutes. This way.
Okay, fine. Okay. Carry on, please.
Okay. But this is a back-to-back awards, and also Federal Highway based on the concept, they divide into 3 different conditions. If this is space is small, that basically there's no external force. If the space is getting larger, and they will be independent. Okay. But we did the analysis as well with numerical limit equilibrium method, and we find out actually the numerical method, limit equilibrium method, especially with Spencer method, they match pretty well. Okay, and even you don't have the space in between, you still have an external force. Okay, now for this case, the limit equilibrium method does not do very well as a numerical method because the limit equilibrium method only can analyze one side of failure. But in reality, you have to have 2 sides. But here basically show you some difference. Federal High, basically the interaction very small, but in reality, their interactions much larger, okay? For both soil. I just move fast down here. Now, how about a limit space situation? And this is a limit space. Basically, if you have a bedrock, and then in front there's reinforced fields, and we use the limit equilibrium method or numerical method to back calculate the force required to maintain the stability, and it match pretty well. Now, one thing I want to point out, that people may think that this is reinforced very narrow field material. You may expect the earth pressure very small. Actually, it's not. This is like even 1/10 of the field of the wall height. You still have like 50%. This is why for this retaining wall, they designed underestimate, okay, the force. Okay, this is dealing with the secondary reinforcement, and there's no design method, but this is a primary reinforcement. This is a secondary reinforcement situation. Okay, how do we design? No design method. Okay, now let me move on to the unified limit equilibrium method. The concept is very simple, just similar like a Bishop method or wedge. But if we want to maintain the stability of this wedge, the normal shear stress, then we need the tension in the geosynthetics, right? And then we have a formula to calculate force, and we assume effect safety equal to 1. And then if you have a more than 1 requirement, you divide by effect safety, and then we can check each failure plan. Then we can calculate what the required tension at the different failure plan. But that's for 1 layer. How about 2 layers? For 2 layers, we can calculate the same force and divide by each layers. Remember, for limit equilibrium, we assume the 2 reinforcement carry the same force. Then for this case, okay, same thing, I go fast. But you have 2 layers. You see, like this, okay? Now, then we design, of course, we need to satisfy 1 layer and 2 layers. Let's start with the 1 layer again, then 2 layers we have, then we plus together like this, okay? Now, we need to make some adjustment here in order to satisfy both layers, because this one is for first layers, this one's for second layers. Because the first layer already carry more load, the second layer you don't need to carry that much load. But this is for second layer, you need to carry extra load. Eventually, you get this kind of requirement, okay? Okay, but this is called top-down design method procedure, continue from top to all the layer analyze. But now let's say based on the analysis, we need to require this tension. In order to meet the requirement, we need to make sure that the front, the back meet the requirement. From front, your reinforcement should be longer enough to prevent the pull-off. In the front, how do we do that? But we have to have a connection force. This is how we determine the connection force. And at the top, we need enough tensile force. But eventually, we get this kind of design joint, okay? In the front, connection force, reinforced length, then total stress, okay? But this is the basic requirement to design for retaining wall. Now, the one I show you with a planar failure plan, but you can do circular, you can do log spiral, it goes fast. Show you some example. This is the one with a vertical wall. You see the required tension in the geosyncline there with the limit equilibrium. Now, one important thing for this method, we can determine what the connection force requirement, 40%. AASHTO always assume 100% because we cannot, based on all the method, retaining wall method, we cannot calculate, but only assume 100%, okay? Now, this is the case basically very similar to the retaining wall slope for the airport in India. Bottom of the wall, top slope, we can calculate based on this method, right? And this is the case dealing with secondary reinforcement. You see that the small reinforcement, we can calculate tension. Primary reinforcement, we also can calculate tension. I'm almost done, okay? And also, you can check with the footings. If you have a footing on the top, this is without footing, this is with footing. And as you can see, without footing is 10 kilonewton per meter for each layers. With footing is 15 kilonewton per meter because you need to carry load. But this is basically the summary of this method. It is a top-down design method. But use a modified field friction angle, basically if friction divided by effect safety, and then determine minimal required tensile force to satisfy limit equilibrium, and then check the real pore capacity ensures the reinforced length, check the front pore to determine connection strength, and then select geosyncline meet the strength requirement, okay? But this is a unified method for slope in the walls to address internal, local, and global stability, can analyze from almost all the situation. But if you are interested in this method, there's a Federal Highway publication, okay, published by Professor Dovnishitsky. You can take a look at that. With that, I reached the conclusion remark. I'm sorry, I ran very fast. The geosyncline-reinforced field wall slope, including those under special conditions with what we talked about, have been successfully used for many projects. The field wall slope have been artificially divided by a slope angle designed with different method, which result different reinforcement requirement for current situation. The field wall slope actually have the same failure mechanism, which can describe by the limit equilibrium concept. But the unified limit equilibrium method can be used to analyze the stability of geosyncline reinforced field wall and slope under different conditions without artificial division and modification. Thank you very much.
That was great, sir. You finished well on time. Thank you. And you covered everything. Yes, there are many questions, I'm sure. I will take that up later.
Okay.
Professor Gandhi?
Professor Bagley, would you like to give some quick summary of
Oh, yeah, sure. Why not? In fact, that would be great. In fact, Professor Han, I think you've really put everything in a nutshell in just a matter of hardly 20, 25 minutes. I really admire you, and I'm sure even Professor G.V. Rao would appreciate it because together we are working on a code of practice in India for this very same topic.
Okay.
Professor Han, you've very well brought out the history of reinforced soil, including the Great Wall of China. I would even like to add the walls of Babylon also. Well, in any case, it will be a little biased from my side. Then you have really brought out the aspect of the difference between analysis and design. Yes, that was really wonderful. The difference between a wall and a slope and how numerical analysis can unify the definition of wall and slope. You need not worry whether you've got a wall or a slope in your hand. And then, of course, the importance of the secondary reinforcement also. Very well brought out pictorially. Thank you, Professor Han. We really appreciate it. Thank you.
Thank you for your summary. Very nice. Thank you. Thank you for the opportunity. Okay. Let me stop sharing here.
Thank you, Professor Han, again.
Sir, can I seek one clarification? Hello?
Okay. Professor Rao.
What is the main difference between the latest edition of AASHTO and the other one, previous ones?
You mean AASHTO and the Federal Highway?
Yeah. The latest one.
Latest one, AASHTO basically now include the 4 different methods, include the limit equilibrium method. Used to be, we don't have that method. We use a simplified method, basically the ladder earth pressure method. But that's a different. The federal highway and the AASHTO is different. The AASHTO is like a standard. Federal highway is a government document. It's different.